This is the tutorial on Model Predictive Path Integral Control. So the method of Model Predictive Path Integral Control, or MPPI for short, was first presented in a 2015 publication titled Model Predictive Path Integral Control using covariance variable importance sampling, so you can check it up if you'd like to. And we'll consider the application case of an RC race car driving around a sand track. As you can see in this picture, it was also developed at the same group that published this paper. And the RC car will serve as our working example to really show you how MPPI works. So let's look at the problem we're trying to solve. We would like to be able to control some nonlinear system that's subject to specific disturbances. So here's the system that has some process noise. In our case, it's the RC race car, which has a state which is encoded by a position and a velocity. And the system evolves according to some partial differential equation. In this case, it has a nonlinear term that can be pretty much arbitrary. And the dynamics are affine in control, and it has an affine disturbance added on top. So this kind of system evolution law can be fit to a lot of realistic processes, but of course not all of them. So the system admits some state. For example, at some sample time step k, it would be a state xk, but we don't have access to it. So we need a sensor that provides some information about the state, but usually sensors are imperfect, so the sensor gives us some noisy measurement, where zeta k would be some kind of noise added on top. With those measurements, we can feed those into a controller. In our case, the controller will be the MPPI controller. The controller also needs to have some access to a cost function to decide which states it should lead the system to and which it shouldn't. And the output of the controller is some input UK that can be fed into the system. Then the system evolves to the next state. You can sample a new state and repeat the procedure. So that's the whole setting that we want to apply MPPI on. Let's look at the core ideas behind MPPI control. It's a model predictive control algorithm, and the core principle behind it is that you can simulate, using a model of the system, thousands of trajectories into the future. So you really try to simulate lots of different inputs and see what would happen to the system if you actually applied them. And the way those inputs of each of those thousands of rollouts that you produce is different is that they are somewhat randomized. So you really produce lots of random inputs, apply them to your system model, observe what you would expect to see, and see if that is good or bad. That's basically the whole idea behind it. And to determine what inputs are kind of the best of those that you've tried, you use a weighted sum of, actually you weight the inputs that you did try. And how you do that? Well, the idea is that if you simulate it to the future and what happens according to your model is very good, it has, for example, low cost, then the inputs that produce this very good low cost trajectory, those inputs must be very good. So we should weight them very much in the update. And that's a very intuitive assumption, and that will really help understand why the update law of MPPI is the way it is. And we'll see that in just a second. But bear this kind of principle in mind. Then you can update the inputs according to this update law that we'll see in a second, and you have to repeat this procedure over and over again. So let's look again at the same example, the race car, and it has a state at a certain position right now, and it has a velocity. And what we do is we select an MPC horizon. So in this case, we want to say that we optimize over the next 4 steps. We want to see what would happen in the next 4 time steps and try to find the best inputs that would result in the best trajectory of those 4 steps. Normally, we would do this with thousands of rollouts, but right now we're going to consider 3 rollouts. So we do 3 simulations into the future. And to do that, we need to draw 3 random vectors of disturbances. Those can be Gaussians, for example. And we'll denote them with delta UK. So K is the index of the rollout. And in this case, it can be 1, 2, or 3. And each of those delta U vectors has 4 entries, so 4 elements, because you need one separate disturbance for each horizon step. Okay, so we'll try those 3 rollouts. Every one of them gets a separate color. And in the kth rollout, we apply a disturbed input vector, U plus delta UK. So all those perturbed input vectors share this component U, or share this vector U, but on top of that vector, we add this random noise vector. And again, that combined vector is really the input that we apply to the system, and it's again a 4-component vector. And this vector U is the so-called vector of nominal inputs. It's the vector of inputs that we kind of pass from each iteration to the next. And that's the vector that we want to update. So let's apply the first rollout, or let's see what happens. So we draw the first set of random inputs, and we see, okay, the rollout actually leads the car off the track. Well, how did we get there? Well, let's look at this. So this is the input U of rollout number 1. And index 0, so that's kind of the 0th entry of that vector. Then we land here. In that state, we apply of rollout 1 of the vector, the first entry, and we land here. Then we do that again for the next entry of that vector and the last entry of that vector. Now we've applied all those inputs and we land in this final state. Over the time of that state evolution, we accrue a cost of 2,000. Now we do the same thing again for the second rollout, so the second set of randomized inputs. And we can see that actually now we land in this state on the first input. Then we apply the next one, so this time it's the input of rollout 2 and component with index 1. We land in this state, we take the next input component, we land in this state, and the next, and we land in this state. In this case, this trajectory, the purple one, resulted in a very low cost of 100, because we stayed on the track perfectly and probably even at a high speed. The third rollout doesn't look that good, so the sets of inputs that make up the third rollout actually produce a very bad trajectory, and we end up in this state. The cost of it is 5,000 of that rollout, so that's very bad. So what is the update law that we're talking about? Well, in MPPI, you want to update this vector of nominal inputs in every iteration. And how do you do that? Well, you update the nominal input vector as U equals U plus a sum of weighted perturbations. So you take these perturbation vectors that you have drawn before to produce the rollouts, and you sum them using a weight. And then you normalize that weighted sum by the sum of the weights to really make the weights sum up to 1. What do the weights look like? Well, the weights are e to the minus 1 over lambda times sk. Sk is the cost of trajectory k. So in this case, sk is 2,000, then 100, then 5,000. And lambda is some constant parameter that we can choose. Okay, let's look at this example. What would we get? Well, we would update using lambda equal to 1 just for simplifications. We would update U as U plus e to the minus 2,000 times delta U1, 2,000 being the cost of it, of the first trajectory, delta U1 being the perturbations that made up that first trajectory, plus e to the minus 100, 100 being that cost, times the perturbation delta U2, and plus e to the minus 5,000 with that cost, times delta U3. And then normalize it with the sum of those weights. And what we can see directly is the low cost trajectory gets the largest weight, by far the largest weight, because e to the minus 100 is much larger than e to the minus 2,000, relatively speaking. So actually low cost means large weight. And that makes intuitive sense. It goes back to this idea that a low cost rollout says that the inputs that produce this rollout should get a large weight. And we normalize the weights as I just said. So as you can see, the bad rollout actually gets a really small weight, and it basically has no influence on the result. Going back to our motivation or problem setting, well, this is the setting that we're given, as we've just seen. And this paper by Williams that I've just shown in the beginning, its main contributions are as follows. So they start with this PDE of the dynamics with the assumptions that I've mentioned. And they apply the so-called path integral control framework, which allows us to transform the solution of that PDE into a solution where you have to calculate expectation values. And when you have a solution that's made up of expectation values, you can actually solve those in a real-world problem using Monte Carlo sampling. And a really great addition to the work is, and very important is, that they don't use standard Monte Carlo sampling, but actually so-called importance sampling, which is a trick to make those solutions with Monte Carlo much faster to get to a really good solution. So that's an important ingredient also to this method. Then they of course have to discretize the solution, because the derivation is mainly in continuous time, but of course a real-world system works in discrete time. And in the end, there are some limiting or simplifying assumptions on the system and the cost structure and everything that make this control and update law really shrink down to this very simple form that we've just seen. It's definitely not admissible for every single system, but given these assumptions, it becomes very simple. That's why it's so elegant. And the update law is just shown here once more. So U is updated as U plus. And then this was a sum of weighted perturbations. And in reality, of course, it's not a sum, but an expectation. And we just solved that expectation using, in our past case, 3 Monte Carlo samples, basically. But of course, to get a good Monte Carlo estimate, you should use thousands. And that's what they are. The rollouts that we're talking about are actually Monte Carlo samples. And that's a really interesting insight. Another insight is that the only reason why it makes this whole control methodology make sense is that you can actually compute these thousands of rollouts, all these shooting trajectories into the future in computation. You can only do that in real time because you have nowadays access to GPUs and parallel computation. If you weren't able to do this in parallel, it wouldn't make sense to use it, for example, on a race car. So this is the race car again. You can see how it's driving around the track at a pretty high speed. And you can also see how the sand provides very unforeseeable disturbances. And this car is actually equipped with a couple of sensors. So it has a measurement unit internally, it has rotation sensors on the wheels, it has GPS, and it has stereo camera vision. And to be able to compute all these MPPI rollouts, it actually also has pretty high compute power on board. So it has a large RAM, and it also has a graphics processing unit on board. So in the bottom left, you can actually see how these rollouts, every one of the rollouts in computation are one of those white lines. And so because there are thousands of them in this real experiment, you can actually only see this kind of cone of exploration. And you can see that by randomly changing inputs on these future paths, you can actually generate a widening cone of where the car should end up. And those computations are made using a trained model of the environment. Of course, there's no access to a perfect model, but using some kind of imperfect trained model, you can really do these computations and view what the controller sees, right? So you can really see this cone of trajectories that you can that you're exploring, and how with this weighted sum, you kind of the controller kind of decides on some line in the middle of that. Let's look at the algorithm again in more detail and understand how this translated into code. The first thing you have to do is to initialize a control sequence, and this is the sequence of nominal inputs. It has indices 0 to n-1, n being the MPC horizon. So it's a vector of n components. In our case, n was 4, so we have MPC steps 0, 1, 2, and 3, which are plotted here on the horizontal axis. And the vertical axis in this plot shows the magnitude or the value of the control input. And here we initialize the nominal control sequence as these black dots, just as zeros. Now we start a loop that doesn't end until we basically decide to end it. The first thing you have to do every time you loop, you generate these random perturbations that we've seen, so these delta U's. And then you use these delta U's to generate the inputs that you'll apply to the system. Now you take every one of the Monte Carlo rollouts. In our case, capital K was 3. So we have 3 Monte Carlo rollouts where we do this following thing. So we start in the current state, x of 0, and then we simulate the MPC horizon. So we go through the MPC horizon steps 0 to capital n-1, and we calculate the input, which is the nominal input plus the disturbance vector that's drawn for this Monte Carlo rollout. Then we calculate what the next state should be according to some model that we have access to, and we can feed the model the state and the input, and it should output us the next state. And on the way, on the next state, we actually now have access to some kind of cost, because the state results in some kind of stage cost that we can see here. And the input also has an influence on the stage cost. And we add the stage cost onto the rollout cost. So this is the total cost of this trajectory, and we kind of make it a sum of the single stage costs. So as you can see in the very beginning, we started at a cost of 0. Now we applied this input, we land in this state, and we've accrued a cost of 400. Now here in computation, we apply the second input, which is now plotted here. So this is the input of the MPC step 1. We apply it, we land here, and we added something onto the cost. Now we're at 1,200, which is kind of bad because we just got off the track. Now we generate the next input, it's just applied here, and we can see this is the next input. And we end up in this state, and we actually added something on top of the cost. And then we do this a final time, so we apply a new input, which you can see plotted here, and we land at the state, and that's how we get to this 2,000 cost for the rollout. We can do the same thing again for the second rollout, right? So we can generate those inputs and apply them, and we can accrue the cost step by step. In this case, we see that the inputs that were done now are kind of different from the first rollout, and we can see that this difference must have caused the car actually to admit better states. And doing it a third time, we have new samples of inputs. Now this time the samples are kind of out of luck, because the inputs that we draw here in red, they are actually pretty bad and lead the car off the track, right? So we got a 5,000 cost. After doing all our rollouts, we're now done doing this outer for loop, which of course in practice would be a parallel computation. And then we can update the inputs. We can now use the update law that we've talked about. So for every one of those horizon steps, we can update the corresponding input of that nominal vector using this update law of reward weighted perturbations. And that again is U plus weighted sum of perturbations. And how this would look is, so we have this nominal set of inputs, and now we shift it towards inputs that produced low cost. So in this case, the purple dots really are the most influential. They carry the largest weight, by far the largest weight. So the nominal inputs will kind of interpolate in an interpolation way, shift to these good inputs. So we'll shift there, not quite exactly, because the other inputs also have an influence, but just a very little one. So here the nominal input will shift down here. Here the nominal input will shift somewhere here. And here the nominal input will barely move because it's already very close to the input that caused a very good trajectory. So now you are kind of done with the update. Now you have this set of nominal inputs. You pick out the first one, so U0, and you apply it. And then you kind of apply it to the system. You wait for the system to evolve for some time step, and you're now in the next state. And hopefully you are where you expect it to be. And now you've used this first input, you can discard it now. And what you now have is actually three other nominal inputs that are now not zero, because we've actually already used some knowledge about the previous rollouts that kind of told us something about what these values should be. So we are going to preserve them and use them for the next iteration as nominal rollouts. So we will basically, to preserve this plot, we would now shift these values one index to the left and generate a new nominal input here at 0 again. Now we're here, we've done everything we had to do for this iteration. We check if the task was completed. In this case it wasn't, so we're now at this state, and we repeat the whole thing again, drawing new random samples, doing new Monte Carlo rollouts, and doing new nominal updates. And that's really how it goes, right? So this is the control law that's applied every single time, the updates that are done every time, the optimization using lots of samples. And I hope that this will make it much clearer reading the code, maybe I'm trying to understand the algorithm. And yeah. So now's your turn. We've added an MPPI controller to the card pull simulation environment. And it comes with this pop-up window that lets you adjust a lot of parameters of MPPI. So MPPI has some parameters that govern, for example, this lambda, that have influence on the cost and the weights. Then you have, of course, a cost function that you can tune. So this cost function, for example, has a couple of components where you can use the sliders to increase or decrease the importance of that component on the total cost. And for example, if you increase the weight of this cost, it will penalize more strongly a difference to the target position. So the card will move more aggressively to the target position because it wants to decrease that cost as quickly as possible. Also, you'll find further parameters down here to adjust, for example, also the variance of those delta U's. So you can, of course, make a difference between exploring very widely or exploring in a narrow field, and you can do all that in this pop-up box. Also, you can change the type of samples you can produce, for example, IID Gaussians, but you can also choose to try out some other sampling procedures to generate those delta U's. Okay, so get cracking. The link is posted here.